The last two periodic trends that we're going to talk about are electron affinity and electronegativity. I'm going to put these two kind of close together in the same discussion because they're kind of close in terms of meaning. They are not exactly the same, but they are more or less the same. So let me give you the more or less definition of electron affinity. It is the opposite of ionization energy. Ionization energy was the energy required to remove an electron. So electron affinity is going to be the energy gain from trying to give or add an electron to an atom. Ionization energy was to make positive. Electron affinity is to make negative. Not all elements want to become negative. There is also an equation associated with this, similar to the one in ionization energy. Again, if we have element X, we are going to try and add an electron to this element, and the result of that will be, this time, a negative ion. This time the energy change will be negative. It is an exothermic process. Again, that's an exothermic process. You can kind of consider it as, maybe the atoms are giving you a little bit of a thank you by returning some energy when you give them an electron. One question you might already have is, well, if it's exothermic, then why the heck are the numbers on this screen up here, why are they not negative? Why are they positive? Well, the answer to that is they've just taken the absolute value of the heat amounts, the energy amounts that you actually measured. And they really want a periodic table full of negative numbers. So it's just an absolute value. If you look at hydrogen, 73.5 is the number value. So what that means is when I give hydrogen an electron, it says thank you, and in return it kind of kicks back 73.5 joules of energy. The higher that number is, the more thankful the element is to be receiving an extra electron. Let's go across to the right-hand side. Look at fluorine. Fluorine has an electron affinity of 331.4. That's pretty high. Fluorine is pretty happy to be receiving this electron. That would make sense. Fluorine has 7 valence. It really wanted another one, so it's really thankful for the gift. You might have been kind of peeping ahead. I haven't really talked about the trend yet, but the white elephant here, or maybe just the elephant in the room, whatever, mixed metaphors, is nitrogen having a value of -7. You're like, well, I thought you just said you can't have negative numbers. No, I said they took the absolute value of the negative numbers for most of them, but the nitrogen is opposite. What that's saying is that nitrogen actually fights against being given an extra electron. It doesn't want it. Nitrogen has the 3 electrons into the px, the py, and the pz orbitals. There's one each in there. It doesn't want another one because then it would have to be paired up. So you're going to have a bit of an energy deficit trying to make that happen and trying to make 2 electrons pair up in an orbital. Another fairly obvious thing, if you look at the chart, is that the alkaline earth metals and the noble gases do not have values for electron affinity. Those atoms do not take electrons. There's nowhere for them to be. The noble gases are full valence. They have 8, so there's nowhere for a 9th one to stick. It's not going to happen. And the same goes to the alkaline earths. Their s orbital is full. They're not going to be sticking an electron into a p. So take a quick look yourself and see if you can identify the trend. This trend is actually the same as ionization energy. The electron affinity decreases as you go down a column for more or less the same reasons as ionization energy. The electrons get further away, so they're going to be less thankful to receive more electrons. They're harder to hold. The further away they are, the harder they are to hold into place. So francium is not really looking forward to extras. As you go from left to right across a period, the value increases just like it did for ionization energy. The atoms are more thankful. They are more willing to take in an additional electron, and that goes toward completing their valence shell. Now let's move on to probably the most immediately useful of the trends to us in chemistry. Electronegativity is, by definition, very similar to electron affinity. It has to do also with attracting an electron or getting another electron. But there is one very subtle but powerful difference, and here it is. Here's that difference. Electronegativity has to do with an atom's pull or attraction for electrons, and here it is, in a bond. So for electron affinity, you're looking at just atoms and atoms gaining electrons. For electronegativity, a bond has already formed, and now, after the fact, you're looking for how hard the nucleus of one atom is pulling on the shared pair or the shared electron. Okay, that's a subtle but very powerful difference between the two. The trend is absolutely the same. As you go down a column, in every column, the electronegativity decreases. Again, it's very difficult to hold additional electrons that, when you get really far from the nucleus, so those atoms are going to have very low desire to do so. As you go to the right, the electronegativity value increases. The atoms are going to increasingly want to have an additional electron. Don't be the person to miss what I'm about to say. Notice that the noble gases are not there. The noble gases do not have an electronegativity. It's not zero. They don't have one. These aren't energy values, and that's an important thing to understand about electronegativity. For ionization energy and electron affinity, you can actually go into the lab, do those things, add an electron, take away an electron, and measure the energy changes. Well, with electronegativity, these numbers don't really reflect a measured value. These are scales. These numbers are rankings based on a formula that Linus Pauling came up with, I believe, in the 1930s or 1940s. It's kind of like the BCS rankings in football. You get a number, but what do they really mean? They're just kind of relative. Fluorine has the highest value of all the elements at a 4.0. Fluorine was assigned 4.0. And then all the other elements are given a value based on how it compares to fluorine. Oxygen, and it's important to remember for this year in chemistry, is number 2. Oxygen then will be the boss of almost all the elements except fluorine. And then we have a tie for third place. Chlorine and nitrogen are both 3.0. It means they both love electrons and are very happy to add more. And then you can see the trend going back down into the left toward francium in a decreasing way. Again, electronegativity is very important for us. We're going to use this single trend right here to explain ionic bonding, covalent bonding, and the polarity of molecules. We're going to be coming back to this one again and again and again. It's very important for you to remember where the most electronegative elements are.